For billions of years, humanity has gazed at the night sky, charting the stars, mapping galaxies, and ultimately seeking the origin of everything. We've built cosmic narratives, grand stories of creation, all converging on a singular event, the Big Bang. But what if everything we believe about that primal thunderclap, that genesis of space and time, is fundamentally incomplete? What if the universe we inhabit, with its endless expanse of galaxies, stars, and swirling nebulae, is not an ultimate beginning, but merely a colossal echo, born from an event hidden within another reality? Imagine, not a boundless emptiness blossoming into light, but an inconceivable point of infinite density, a singularity, collapsing within an alien cosmos. From that crushing embrace, a universe like ours could erupt, not into the emptiness of nothing, but into a new, boundless dimension of space and time. This isn't mere science fiction. It's a cutting-edge hypothesis, deconstructing our very location in the cosmos, challenging the boundaries of reality, and forcing us to confront the shocking possibility that we are living inside a black hole. We will demystify black holes, singularities, and the Big Bang, revealing how they intertwine in a radical vision of nested universes. Prepare to question everything you thought you knew about where we truly reside. If you're ready to explore the universe within a universe, hit that like button and subscribe. Prepare yourselves, we begin. The universe, in its boundless indifference, has etched a fundamental law into the very geometry of existence, a cosmic speed limit. It is not merely an incredibly swift velocity, but an absolute, unyielding barrier that dictates the parameters of physical reality itself. At its heart lies the speed of light in a vacuum, a constant denoted by c, precisely 299,792,458 meters per second. This isn't a suggestion or a challenge. It is a decree, a universal constant that binds every particle of matter, every flicker of energy, and most profoundly, every hope of interstellar travel for humanity. Before the dawn of modern physics, the speed of light was a subject of intense speculation, a phantom velocity whose true nature remained elusive. Galileo Galilei, in the 17th century, attempted to measure it using lanterns and human reaction times. A testament to humanity's early curiosity, but an inevitably futile endeavour against such staggering swiftness. It took the astronomical observations of old Roma, noting discrepancies in Jupiter's moon eclipses, to provide the first quantitative estimate, revealing light's finite, albeit immense, velocity. Yet, even then, light was perceived as something that travelled through a medium, much like sound through air or waves through water. The 19th century brought James Clerk Maxwell's revolutionary equations, which unified electricity and magnetism, predicting that light itself was an electromagnetic wave propagating at a specific fixed speed. This mathematical elegance, however, introduced a profound conceptual dilemma. If light was a wave, what was its medium? Scientists postulated a ubiquitous, invisible substance permeating all of space, the luminiferous ether. This hypothetical ether was thought to provide the absolute reference frame against which all velocities, including light's, could be measured. It seemed to offer a comforting anchor in a relativistic universe. Then came the pivotal experiment of Albert Michelson and Edward Morley in 1887. Their intricate interferometer, designed with astonishing precision for its era, sought to detect Earth's motion through this supposed ether. They reasoned that light travelling with the Earth's motion through the ether, and light travelling against it, should exhibit subtle differences in speed, measurable as interference patterns. Yet, no matter how they oriented their apparatus, no matter the season, the result was always the same, a perfect null. Light's speed appeared utterly invariant regardless of the observer's motion. The ether, it seemed, did not exist. This experimental triumph was, for many, a theoretical disaster, undermining centuries of physical intuition and leaving a gaping wound in the heart of classical mechanics. It was into this conceptual void that a young patent clerk named Albert Einstein stepped in 1905, not with a new theory of light, but with a radical reinterpretation of space and time themselves. His special theory of relativity rested on two audacious postulates. The first stated that the laws of physics are the same for all observers in uniform motion relative to one another. The second, and most critical for our understanding of cosmic limits, declared that the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source or the observer. This was not merely an empirical observation, it was a foundational principle, an absolute truth woven into the very fabric of space-time. This second postulate fundamentally redefines what speed truly means in the cosmos. Light does not simply move through space, it is the maximum rate at which information, energy and causality can propagate within space-time. It is not analogous to a car's speed limit on a highway, which can be broken, or even a sound barrier, which engineers can overcome. Instead, it's akin to a fundamental parameter of the universe's operating system, an intrinsic property of the four-dimensional space-time continuum itself. Every particle, every field, every interaction ultimately defers to this speed. It is the cosmic constant that binds all reality, making it an inescapable ceiling for anything with mass. To grasp the profound nature of this barrier, consider a thought experiment. Imagine space-time as a vast, frictionless ocean. Everything within this ocean is constantly in motion through its four dimensions, 3 of space and 1 of time. An object at rest, relative to us, is actually moving entirely through the time dimension at the speed of light. As it begins to move through space, some of that velocity is diverted from the time dimension into the spatial dimensions. The faster an object moves through space, the slower it moves through time. Maintaining its total speed through space-time at exactly c, to reach the speed of light in space would mean diverting all motion from the time dimension, effectively stopping time for that object. But this metaphor only hints at the truly unyielding nature of the barrier, because the universe enforces this dynamic with a suite of consequences that are nothing short of absolute. The implications of Einstein's decree are not abstract mathematical curiosities, they are physical realities that manifest as profound paradoxes for anything attempting to approach light speed. As an object accelerates, its mass does not remain constant. Instead, it increases dramatically. This isn't a gain of new matter, it's a consequence of its increasing kinetic energy being converted into relativistic mass. The closer an object gets to the speed of light, the more massive it becomes, demanding exponentially more energy to achieve even tiny increments of speed. To reach c itself, an object with any rest mass would require an infinite amount of energy to accelerate its mass, which would have grown to an infinite extent. The universe simply does not possess enough energy to propel even a single atom to light speed. This is the first, and perhaps most devastating prison bar, an unbreachable wall of infinite mass and energy. Beyond the theoretical impossibility, the practical consequences of merely approaching. This cosmic speed limit are equally grim, transforming the vast, seemingly empty stretches of space into an unimaginably lethal environment. Even the most negligible particles of interstellar dust, normally harmless, become weapons of catastrophic potential. A grain of sand, tiny and innocuous on Earth, if encountered by a spacecraft travelling at a significant fraction of light speed, would impact with the energy of a nuclear bomb. The kinetic energy of any object scales quadratically with velocity. As velocity rockets towards c, this energy becomes astronomical, turning every stray hydrogen atom, every cosmic ray, every microscopic fragment of ice or rock into a devastating projectile capable of tearing through even the most robust shielding. The vacuum of space, once seen as a serene pathway, becomes a gauntlet of hypervelocity shrapnel, a lethal, unforgiving environment. This immutable barrier, this cosmic decree, casts a long shadow over humanity's dreams of truly conquering the stars. It implies that the vast, breathtaking distances to even our nearest stellar neighbours are not merely a matter of technological progress, but an inherent, unyielding separation. Alpha Centauri, our closest star system, is over 4 light-years away. A journey there, even at velocities approaching c, would stretch across years, decades, or even centuries of subjective time for those remaining on Earth. The speed of light isn't just a limit, it's a profound statement from the universe, reminding us of our cosmic scale and perhaps our permanent confinement. This is the deep, unsettling reality that underpins our attempts to navigate the infinite dark, creating a sense of inescapable cosmic claustrophobia, a recognition that the universe, for all its grandeur, might forever keep its deepest secrets just beyond our reach. If the insurmountable wall of infinite mass is one unyielding prison bar, then time's cruel distortion is its psychological twin, twisting the very fabric of our subjective reality. Einstein's special relativity didn't just tell us we couldn't reach the speed of light. It revealed that the universe itself possesses a malleable clock, one that ticks differently for those who dare to approach its ultimate velocity. This phenomenon, known as time dilation, isn't a futuristic plot device. It's a proven fact, a silent, pervasive force that irrevocably alters our perception of journey and destination, making true interstellar civilization an almost tragic endeavour. Before Einstein, time was considered an absolute universal constant, flowing uniformly for everyone. Everywhere! Isaac Newton's majestic cosmic clock ticked in perfect synchronicity across the vast emptiness, providing a stable, unvarying backdrop against which all events unfolded. This intuitive understanding of time feels natural to our everyday experience, where a second in New York is a second on Mars, and a year on Earth is a year in a distant galaxy. However, this classical view shatters when objects begin to approach the speed of light, exposing a deeper, more fluid reality where time itself becomes relative, stretching and compressing depending on an observer's motion. The essence of time dilation stems directly from Einstein's second postulate, invariant for all observers. To uphold this universal constant, space and time must adjust. Imagine a thought experiment, a light clock, where a photon bounces between two mirrors. For an observer at rest relative to this clock, the photon travels a straight path up and down, but for an observer moving rapidly past this clock, the photon's path appears diagonal, longer, forming a zigzag pattern. Since the speed of light must be the same for both observers, and the moving observer sees the light travel a greater distance, the only way for the speed to remain constant is if the moving observer's time runs slower. Their clock, in effect, ticks more slowly to compensate for the longer path the photon seemingly takes. This isn't an optical illusion or a trick of perception. It is a fundamental alteration of reality itself. Clocks on a rapidly moving spacecraft would genuinely tick slower, relative to clocks on a stationary planet. Biological processes, thought, aging, everything occurring within the moving frame of reference would slow down. From the perspective of the astronauts on board, however, everything would feel perfectly normal. Their heartbeats, their thoughts, the aging of their bodies would proceed at their usual pace relative to their own ship. They would not feel time slowing down for them. Rather, they would observe the universe outside their window rushing by at an accelerated rate. Here lies the cruel distortion, the central paradox that transforms light speed into an existential barrier rather than a mere technological hurdle. For the Voyager, a journey to Alpha Centauri, 4 light-years away, might take a mere subjective handful of years if they accelerate close enough to see. They would experience the trip, live through it, perhaps even raise a family on board, but for their twin, their family, their entire civilization back on Earth, decades, even centuries could have elapsed. They would return to a world transformed, a future that has moved on without them, populated by generations they never knew. The familiar faces, the cherished memories, the very cultural landscape of their home would be irrevocably altered or simply gone. Consider a mission to a star system, 100 light-years away. Even if we could hypothetically achieve 99% of the speed of light, the journey would still take over 101 years for Earthbound observers. But for the intrepid crew on board, time dilation would compress that journey into approximately 14 subjective years. They would depart a familiar Earth, venture into the cosmic abyss, and return to find their home planet 101 years older. Their great-grandchildren, if they had left any, would be elderly or long deceased. The institutions, technologies, and societal norms they knew would have either flourished beyond recognition or crumbled into dust. This isn't just a physical distance, it's a temporal chasm, an unbridgeable gap in human connection that makes true continuous interstellar civilization, where different star systems remain meaningfully linked. A near impossibility. The practical implications of this time distortion are devastating for any sustained human presence across the galaxy. Interstellar communication becomes a conversation with ghosts. A message sent from a colony on a planet 50 light-years away would take half a century to reach Earth. A reply would take another 50 years. This century-long dialogue latency renders real-time interaction meaningless. Commands from Earth would arrive generations after the issues they addressed had either resolved or utterly transformed. Cultural exchange would be a glacial process, with traditions, languages, and ideologies diverging wildly across vast temporal and spatial gulfs. Each star system would become a self-contained, isolated cultural island, developing independently, severed by the relentless march of relative time. This isn't just a theoretical quandary. Time dilation is a phenomenon routinely measured and accounted for in everyday technology. Atomic clocks flown on airplanes tick slightly slower than identical clocks on the ground, precisely as predicted by special relativity. More dramatically, subatomic particles like muons, created in Earth's upper atmosphere by cosmic rays, have extremely short lifespans. If not for time dilation, very few would ever reach the ground. But because they are travelling at relativistic speeds, their internal clocks slow down, extending their observable lifespan from a few microseconds to an extent that allows them to reach detectors at sea level. These are not insignificant effects. They are robust experimental confirmations of Einstein's profound insights. For humanity, these relativistic clocks impose a fundamental limit on our collective reach. Even if we master propulsion, even if we develop impenetrable shields, the universe still ensures that any journey to distant stars will extract an unbearable cost in time. You can choose to experience a short, swift journey to another star, but you implicitly choose to sever ties with your past, to lose everything and everyone you left behind. Or you can embark on a journey that preserves those connections, but it will be a multi-generational voyage, a slow crawl through the cosmic night that would require a complete redefinition of human purpose and societal structure. This is the very essence of the prison bars of light speed. It forces a cruel dichotomy. Either you travel, but at the cost of your past and your civilization, or you stay, forever confined to the temporal synchronicity of your homeworld. The choice isn't freedom or confinement, it's merely a different form of confinement. The universe, in its elegant precision, has made sure that no matter how fast we move, the threads of our existence remain tragically short, preventing us from weaving a cohesive, star-spanning civilization. It ensures that any true galactic empire would be a collection of disconnected, evolving cultures, each adrift on its own relativistic timeline, a testament to humanity's ultimate, unyielding cosmic solitude. This pervasive, unfixable distortion of time is one of the most profound and unsettling limitations to our dreams, a constant, echoing reminder of our inescapable place in the universe. If time itself warps and stretches, becoming a subjective river rather than a universal constant, then the companion paradox of mass inflation acts as an even more formidable, material prison bar, demanding an impossible ransom in energy for every fraction of light speed we dare to approach. This isn't merely an engineering challenge, it is a fundamental, unyielding wall of infinite mass that slams shut the door on true relativistic travel, locking humanity into an inescapable energy deficit. Classical Newtonian physics, the bedrock of our intuitive understanding of the physical world, posits that an object's mass is an inherent, unchangeable property. A kilogram of iron is always a kilogram of iron, whether it sits still on a table or hurtles through space at 1,000,000 miles an hour. This concept holds true for the everyday speeds we experience. However, as velocities begin to push the boundaries of the terrestrial, a profound and counterintuitive truth emerges from the depths of Einstein's special relativity. Mass, like time and space, is not absolute. It is intricately linked to motion, and its behavior near the speed of light becomes an absolute barrier to all acceleration. As an object accelerates to speeds approaching c, its effective mass begins to increase dramatically. This isn't because the object is somehow acquiring more atoms or fundamental particles. Rather, it's a consequence of its kinetic energy being converted into a form of inertial resistance, a relativistic mass that makes it increasingly difficult to accelerate further. The very energy poured into accelerating the object doesn't just make it go faster, it makes it heavier, in terms of its resistance to further changes in motion. Imagine pushing a cart at slow speeds. It responds readily. Now imagine that car inexplicably gaining immense weight the faster you push it, demanding exponentially more effort for each tiny increase in speed. That's the relativistic mass increase in action. The famous equation, EAMC2, often cited for its role in nuclear energy, is fundamentally about the equivalence of mass and energy. It reveals that mass is a form of concentrated energy. When an object with rest mass accelerates, the energy imparted to it doesn't just manifest as kinetic energy in the classical sense. A portion of that energy gets folded into its relativistic mass. As its speed climbs toward the cosmic constant, more and more of the added energy is absorbed into increasing its mass rather than increasing its velocity. It's a vicious self-defeating cycle. The faster you go, the heavier you become, the more energy you need, which in turn makes you even heavier. Consider the exponential energy curve. To reach just 10% of the speed of light, a spacecraft would require a colossal amount of energy, far beyond anything we can currently produce. But to then reach 50% of c, it demands significantly more than 5 times that initial energy. Pushing past 90% of c requires an almost unimaginable surge of power, and each subsequent percentage point demands an order of magnitude increase in energy. The curve doesn't just rise steeply, it rockets skyward, becoming an asymptotic wall. The universe, in its elegant cruelty, ensures that as you approach the speed of light, the energy required to accelerate your mass climbs towards infinity. This is the ultimate, unbreachable prison wall. To put this into terrifying perspective, consider a single human travelling in a compact, efficient spacecraft. To accelerate this relatively tiny mass to even 99% of the speed of light would require energy equivalent to the entire annual energy output of a small star. To reach 99.9% of c would demand the energy output of multiple stars for decades. To truly touch the speed of light, for any object with even the tiniest speck of rest mass, is not just difficult. It's fundamentally impossible. It would necessitate an infinite energy source, something the universe simply does not and cannot provide. This is not a matter of engineering bigger rockets or more efficient fusion drives. It is a direct consequence of the laws of physics themselves. This infinite mass wall presents an insurmountable obstacle, rendering even the most advanced, theoretical propulsion systems utterly inadequate. Even if we could somehow achieve 100% efficiency in converting matter into energy, annihilating entire planets to fuel a single spacecraft, it would still fall laughably short. The energy contained within our entire solar system, if we could harness every joule of it, would barely be enough to accelerate a small probe to a meaningful fraction of light speed, to launch a large, crude vessel on an interstellar journey at relativistic velocities would demand the energy equivalent of converting entire stars into fuel, a feat so cosmically extravagant it borders on the absurd for any single civilization. This barrier is not merely a technological frustration, it's a source of profound cosmic hopelessness. It means that while the stars may call to us, their embrace is forever denied by the very rules of the game. Our most ambitious dreams of galactic colonization, of exploring myriad alien worlds, crash headlong into this unyielding physical reality. We are tethered by the energy demands of our own mass, chained to our stellar neighbourhood by an invisible yet ironclad law. The universe doesn't need to send monstrous beasts or cosmic cataclysms to keep us confined. Its fundamental physics does the job with chilling precision. The infinite mass wall fundamentally dictates the scale of our ambitions. Any truly viable interstellar travel must contend with this reality, forcing us to consider multi-generational voyages that span centuries or millennia, or to abandon the dream of physical travel altogether in favour of digital exploration. There is no circumventing this law with a clever invention, no loophole to exploit. The laws of physics are not suggestions, they are absolute commands, and the command regarding the speed of light is unequivocal. Thou shalt not pass. This deep, unyielding truth instills a sense of profound cosmic claustrophobia, reminding us that for all our ingenuity, we are mere specks, bound by the universe's unyielding, beautiful, and utterly merciless rules. This energy barrier, combined with the temporal disjunction, forms an unbreakable double helix of confinement, but there's another, more immediate threat awaiting any vessel brave or foolish enough to challenge these limits. If the infinite mass wall and time's relentless distortion are the theoretical chains binding us to our cosmic cradle, then the universe offers a far more visceral immediate threat to any who dare approach its ultimate speed limit: cosmic shrapnel. The vast, serene emptiness between stars, often romanticized as a boundless highway, transforms into an unimaginably lethal gauntlet where even the most microscopic speck of dust becomes a weapon of mass annihilation. This isn't science fiction. It is a brutal, inescapable consequence of physics, rendering interstellar travel a suicidal endeavor. Our intuitive understanding of collisions comes from everyday experience. A car hitting a pebble, a bullet striking a target. The damage depends on the mass and the speed. But these interactions occur at velocities so far removed from the speed of light that they barely scratch the surface of relativistic mechanics. The crucial principle at play is kinetic energy, described by the formula E Jaka 122mv2. While mass, m, contributes, it is the velocity, v, that holds the true power as it is squared in the equation. Doubling an object's speed quadruples its kinetic energy. Tripling it increases the energy ninefold. As velocity approaches the speed of light, this energy scales to terrifying astronomical proportions, turning even a single atom into a cosmic hammer blow. The interstellar medium, the seemingly empty space between star systems, is anything but a perfect vacuum. It is sparsely populated, yes, but not entirely devoid of matter. It teems with diffuse hydrogen and helium atoms, cosmic rays, and microscopic dust grains, minute fragments of rock, ice, and metallic compounds, often no larger than a smoke particle or a grain of sand. While these particles pose no threat to spacecraft traveling at conventional speeds, they become existential dangers at relativistic velocities. A vessel hurtling at 99.9% the speed of light would encounter these stationary particles with an immense relative velocity, imparting catastrophic energy upon impact. Consider a grain of sand weighing perhaps a milligram. If a spacecraft traveling at 100,000 kilometers per hour, a speed vastly greater than any current human vessel, were to strike it, the impact would be significant, likely causing minor pitting or damage to the outer hull. Now, accelerate that spacecraft to 10% of the speed of light, approximately 108 million kilometers per hour. That same grain of sand would hit with the force of a high-caliber bullet. Increase the speed to just half of light speed, and the impact energy could be compared to a small conventional bomb. But at 99.9% of the speed of light, that seemingly innocuous grain of sand unleashes the energy of a small nuclear explosion. This phenomenon of hyper-relativistic impact isn't merely destructive, it's transformative. Upon striking a spacecraft moving at such extreme speeds, a dust particle doesn't just chip or dent, it vaporizes instantly, along with a portion of the spacecraft's hull, into a superheated plasma. This plasma then radiates intense X-rays and gamma rays, sending shock waves through the ship's structure. The resulting cascade of secondary impacts and radiation would degrade systems, overload sensors, and compromise structural integrity with horrifying efficiency. Even a single, relatively large dust grain could be enough to disable or destroy an entire interstellar vessel, turning the vast expanse of space into an inescapable death trap. The challenge intensifies when considering the sheer number of potential impacts over interstellar distances. A journey to a nearby star, even if only a few light years away, would involve traversing trillions upon trillions of cubic kilometers of interstellar medium. While the average density might be low, perhaps 1 atom per cubic centimeter, or a few dust grains per cubic kilometer, over light-year scales these seemingly sparse particles accumulate into an almost certain gauntlet of impacts. A single hydrogen atom striking a craft at 99.9% C might not be instantly fatal, but it would erode the shielding, contributing to a constant, imperceptible degradation. The cumulative effect of countless subcatastrophic impacts would eventually prove just as deadly as a single, larger one, grinding the spacecraft into oblivion particle by agonizing particle. Designing shielding capable of withstanding such impacts is an engineering impossibility under the laws of physics. No known material, no hypothetical force field, could absorb the kinetic energy of matter colliding at relativistic speeds without catastrophic damage. Even multi-layered Whipple shields, effective against micrometeoroids at interplanetary velocities, would be utterly useless. The energy involved means that the projectile and the shield material would largely annihilate each other, generating a massive energy release that penetrates deeper with each encounter. It's a cosmic game of Russian roulette, where every fleeting moment in the interstellar void brings closer the statistical certainty of destruction from an invisible, unyielding foe. This pervasive threat creates a profound sense of cosmic claustrophobia. The emptiness of space, once seen as an invitation, becomes a vast, silent minefield. The very act of accelerating to speeds necessary for meaningful interstellar travel transforms our environment into an active, implacable enemy. Humanity's dream of racing among the stars is met with the chilling reality that the journey itself is designed to tear any vessel, and its occupants, apart. There is no escaping this truth. It is not an alien force or a rogue black hole that presents the greatest danger. It is the fundamental physics governing the interaction of mass and velocity, turning the universe's own breath into a lethal barrage. The psychological toll on any crew embarking on such a journey would be immense. Every flicker of an instrument, every unexpected vibration, every moment of silence would be fraught with the dread of an unseen, impending impact. The vastness that was once inspiring would become a source of constant gnawing fear, knowing that their vessel is constantly, inevitably, being bombarded by particles that strike with the force of artillery shells. This isn't just a physical barrier, it's a mental one, a grim reminder that the universe, in its elegance, is utterly indifferent to our aspirations and has woven lethal consequences directly into the tapestry of faster-than-light ambition. Even if humanity could magically conjure infinite energy, rendering the mass wall irrelevant, and somehow fashion a shield against the ceaseless barrage of cosmic shrapnel, we would still confront the most ancient, most unyielding prison bar of all, the sheer, unfathomable tyranny of distance. The universe is not merely vast, it is a chasm of light years so profound that our dreams of interstellar civilization shatter against its scale, leaving us adrift in an ocean of cosmic loneliness. Our very unit of cosmic measurement, the light year, stands as a stark testament to this despair. It is not, as often misunderstood, a measure of time, but of distance. The staggering expanse light itself traverses in a single Earth year. At its blistering speed of nearly 300,000 kilometers per second, light could circumnavigate our planet over 7 times in a single second. Yet this incredible velocity, the absolute speed limit of the cosmos, is rendered laughably slow when confronted with the boundless scale of the universe. Consider our immediate neighbourhood. The nearest star system, Alpha Centauri, beckons from a distance of just over 4 light-years. To put this in human terms, if we launched a probe today that could travel at a significant fraction of light speed, say 10%, it would still take over 40 years to reach its destination. For the voyagers on board, time dilation might compress their subjective journey, but for those left behind, decades would pass, a generation would live and die. This is the closest star, a mere astronomical stone's throw away. What then of the true expanse? Our own Milky Way galaxy, a spiral island containing hundreds of billions of stars, stretches an incredible 100,000 light-years from one edge to the other. Even if we could hypothetically travel at speeds approaching c, a journey from one side of our galaxy to the other would take 100,000 years for an external observer. For the relativistic traveller, this might condense into a few centuries, perhaps even decades, but the price is absolute. Their home world, their entire civilization, would have aged by 100 millennia. The entire span of human recorded history, from the first cave paintings to our current digital age, is a mere blink in that colossal temporal abyss. Any attempt to unite a galactic empire under such conditions is a cosmic joke, a tragic fragmentation of purpose and belonging. Then we extend our gaze beyond our galactic home. The Andromeda Galaxy, our majestic sister spiral, is our closest major galactic neighbour, located a staggering 2.5 million light-years away. A signal sent from Earth would take 2.5 million years to reach Andromeda. Any reply would take another 2.5 million years. This is not communication. It is a whisper lost to the winds of eternity. A journey there, even if magically instantaneous for the traveller, would return them to an Earth fundamentally altered by 5 million years of independent evolution, a world unrecognisable. perhaps devoid of humanity entirely. To attempt to physically colonize Andromeda would be to embark on a voyage whose return legatees would find not a welcoming civilization, but perhaps only geological remnants of a long-extinct species. The observable universe itself presents the ultimate nowhere. Spanning some 93 billion light-years in diameter, it is a canvas of unimaginable scale, yet it remains forever beyond our physical grasp. We can observe galaxies billions of light-years away, seeing them as they were billions of years ago, ghosts of a younger cosmos. But to travel to those distant shores is a cosmic impossibility, not just because of the journey's length, but because many of them are receding from us faster than the speed of light due to the expansion of space itself. This is the most insidious aspect of the tyranny of distance. The universe is actively working against our expansion. Driven by dark energy, the fabric of space-time between gravitationally unbound objects is stretching, accelerating its expansion. Distant galaxies are not merely far away, they are accelerating away from us, pulling farther out of reach with every passing moment. There is a cosmic horizon beyond which objects recede faster than light, meaning that even if we could instantaneously jump to their location, by the time we arrived they would already be further away, forever out of reach. For humanity, this means that the observable universe is not a potential playground, but a shrinking cage. Many of the galaxies we see today will, in the far cosmic future, disappear beyond our horizon, leaving future civilizations in an increasingly empty sky, utterly isolated. This boundless expanse, therefore, becomes a form of cosmic claustrophobia. We are trapped in a local bubble, our aspirations to explore and colonize the galaxy reduced to a tragic fantasy. The distances are not merely large numbers, they are unyielding separators, ensuring that humanity, for all its ingenuity, remains an insular, solitary species. Any attempt to build a true galactic civilization, where different star systems maintain coherent cultural or political ties, is doomed by the sheer scale of the cosmos and the immutable speed limit of light. Each star system would become an independent island, its inhabitants forever severed from their origins by oceans of light years and the relentless march of subjective time. The universe, in its elegant design, has built an ultimate unyielding prison out of its own boundless expanse. The tyranny of distance, a cosmic chasm that isolates us physically, finds its insidious echo in the realm of communication, transforming the vast interstellar canvas into a realm of profound, unbreachable silence. Even if we could physically endure the journey to distant stars, the speed of a light dictates that any meaningful dialogue across these gulfs is a tragic fantasy, condemning humanity to an inescapable, deeply isolating cosmic solitude. Our universe, it seems, is not designed for conversation. Every signal we send, every electromagnetic pulse carrying our hopes and inquiries, is fundamentally bound by the cosmic speed limit of c. Radio waves, laser beams, neutrinos, all forms of information transfer, whether we beam them from Earth or from a distant colony, travel at precisely the speed of light. This isn't merely a technical constraint, it is a profound dictate of causality. No information can travel faster than light, for to do so would break the fundamental laws of physics, allowing for paradoxes where cause could follow effect. This immutable law ensures that every message we dispatch into the void is a slow-motion echo, often arriving long after its sender has changed or faded into history. Consider once more our nearest stellar neighbour, Alpha Centauri, a mere 4 light-years distant. A radio message dispatched from Earth, travelling at light speed, would take over 4 years to reach any potential listener around those stars. An immediate reply, if one were even possible, would then take another 4 years to traverse the same distance back to Earth. This means that a single exchange, a question and its answer, demands a minimum of 8 years. What kind of conversation can be sustained across an 8-year latency? It is not a dialogue. It is a series of fragmented, delayed monologues, each participant speaking into a void, hoping for an eventual outdated response. The immediacy that defines human connection, the rapid back and forth of genuine interaction, is utterly obliterated by this cosmic delay. For more ambitious interstellar endeavours, the problem scales into the realm of the absurd. A human colony established on a planet orbiting a star 50 light-years away would operate under a communication delay of a century for a round trip. Imagine a central government on Earth attempting to govern, coordinate, or even meaningfully interact with such a distant outpost. Decisions made on Earth in response to a crisis reported by the colony would arrive decades after the crisis had unfolded, resolved itself, or, more likely, escalated into irreversible catastrophe. The very notion of a cohesive interstellar empire, with unified command and shared culture, collapses under the weight of these immutable light-speed lags. Each colony becomes a de facto independent entity, its inhabitants forced to rely entirely on their local resources and judgment, severed from their origins by vast oceans of time. This inherent isolation isn't just a challenge for governance, it poses a profound threat to cultural cohesion and the very continuity of human civilization across the stars. Languages would diverge, customs would evolve independently, technological paths would branch. Over centuries and millennia, a colony might develop an entirely distinct culture, one that shares little more than a distant ancestry with the originating civilization. The concept of home would lose all meaning, replaced by a multitude of disparate, isolated human societies, each an echo of a bygone past, unable to maintain genuine contemporary connection. The universe, through the simple act of setting a speed limit, becomes a cosmic Tower of Babel, ensuring that disparate groups, though sharing a common origin, are forced into an evolutionary divergence by the sheer inability to communicate in real time. The search for extraterrestrial intelligence, SETI, is perhaps the most poignant testament to this profound isolation. We scan the skies for radio signals, listening for whispers across light years, knowing that any signal we detect would be an ancient echo, a message arriving from a civilization 10,000 light years away, tells us about a species as it existed 10,000 years ago. It could be a thriving empire, a nascent civilization, or a silent graveyard. By the time their signal reaches us, and by the time our reply, if ever sent, reached them, millennia would have passed. The original senders might be long extinct, their star long dead, their entire civilization a forgotten chapter in the cosmic epic. We are, in effect, trying to converse with ghosts, exchanging pleasantries with historical records rather than living beings. This also offers a chilling perspective on the Fermi paradox, the perplexing absence of observable alien life despite the high probability of its existence. Perhaps advanced civilizations are indeed common, but the insurmountable communication delays render them effectively invisible to each other. Each civilization might be trapped within its own Hubble bubble of potential interaction, unable to detect or meaningfully engage with others beyond a relatively narrow temporal and spatial window. The galaxy could be teeming with life, yet remain a collection of isolated islands, each broadcasting into a deafening void, listening for echoes that never quite synchronize. The psychological burden of such isolation is immense. To send a message into the cosmos, knowing that a response, if it ever comes, will be received by future generations, not yourself, or that the intended recipient may have vanished long ago, is to confront a profound form of cosmic hopelessness. It drains the immediacy from discovery, dilutes the joy of connection, and magnifies the sense of existential loneliness. We are left to ponder the vastness not as an invitation, but as an unscalable wall, a silent, indifferent expanse that mocks our attempts at unity. Even the most speculative solutions to interstellar communication, such as quantum entanglement, ultimately offer no true escape from this light-speed prison. While entangled particles appear to instantaneously influence each other regardless of distance, this phenomenon cannot be used to transmit information faster than light. Any attempt to exploit entanglement for FTL communication would still require a classical light-speed channel to establish the measurement basis or decode the message. The universe, it seems, has no loopholes when it comes to the propagation of information and causality. The speed of light remains the absolute, unyielding arbiter of all communication. Ultimately, this inescapable communication latency acts as a silent, invisible cage, confining human civilization not just spatially, but temporally. It ensures that our species, no matter how far we spread, will forever remain a fragmented collection of isolated outposts, each evolving independently, each speaking into a void that only returns echoes of a distant, faded past. The universe, in its elegant design, has made sure that even with the most powerful telescopes and transmitters, we remain fundamentally alone, listening for whispers that are already ancient history and sending our own into a future that will have long moved on. This is the profound, unyielding isolation of interstellar communication, a testament to the cosmic claustrophobia inherent in our reality. The relentless tyranny of distance and the profound isolation of light-speed communication bring us to the very heart of the engineering dilemma: propulsion. Our dreams of starships hurtling across the void are not merely constrained by current technological limitations, they are fundamentally imprisoned by the unyielding laws of physics, rendering even our most ingenious hypothetical engines woefully inadequate for true interstellar conquest. This is propulsion's prison, a cosmic cul-de-sac from which there is no escape for humanity. For centuries, the rocket equation, formulated by Konstantin Tsiolkovsky, has been the guiding principle of space travel. It dictates that to accelerate a spacecraft to a certain velocity, you need an exponential increase in fuel mass. The faster you want to go, or the heavier your payload, the more fuel you need, and that fuel itself has mass, requiring even more fuel to accelerate it. This fundamental constraint has dictated the scale of all space missions, from the Apollo lunar landings to probes sent to the outer solar system. But Tsiolkovsky's equation, while a formidable challenge, is merely a speed bump compared to the relativistic wall. As we attempt to push beyond interplanetary speeds towards relativistic velocities, the simple rocket equation gives way to the far more brutal demands of special relativity. The mass of the spacecraft itself begins to increase in speed. This means that any propulsion system, no matter how efficient, must contend with an ever-increasing inertial mass, requiring an ever-increasing amount of fuel, which in turn becomes heavier, in a self-defeating spiral that asymptotically approaches infinity as velocity approaches c. This is the core of propulsion's prison. The universe demands an infinite energy source to accelerate even a single atom to light speed, a resource that simply does not exist. Consider the most advanced hypothetical propulsion concepts, often touted as the keys to interstellar travel. The fusion rocket, for example, would harness the power of nuclear fusion, far more efficient than chemical rockets. Instead of expelling chemical exhaust, it would accelerate superheated plasma, achieving exhaust velocities orders of magnitude higher. While such an engine could dramatically shorten journeys within our solar system, perhaps reducing a trip to Jupiter from years to months, it still falls far short of the requirements for interstellar travel. To reach even 10% of light speed, a fusion rocket would require a fuel-to-payload ratio so immense that the vessel would be almost entirely fuel, far exceeding any practical design. The sheer scale of fuel needed would necessitate mining entire gas giants for deuterium and helium-3, a feat beyond our current or even plausible future capabilities. Then there's the antimatter rocket, often considered the holy grail of propulsion due to its theoretical maximum efficiency. When matter and antimatter meet, they annihilate, converting 100% of their mass into energy. In accordance with EREMC2, this would offer an exhaust velocity approaching the speed of light itself. If we could generate and store antimatter in sufficient quantities, a spacecraft could theoretically achieve significant fractions of c. However, the practical obstacles are staggering. Producing antimatter is incredibly energy-intensive. Current methods yield only minuscule amounts, requiring vastly more energy input than the antimatter ultimately produces. Storing it safely, preventing it from touching ordinary matter, presents an engineering nightmare, especially for the quantities needed for interstellar travel. A gram of antimatter contains the energy equivalent of a small nuclear bomb. A kilogram could power a major city for years. To propel a manned starship to Alpha Centauri at 50% C would require tens of tons of antimatter, a quantity that represents the energy output of hundreds of thousands of nuclear power plants running for centuries. The production, containment, and safety of such a fuel source are so far beyond our capabilities that it remains firmly in the realm of speculative fiction. Even more exotic proposals, like the interstellar ramjet, envision scooping up hydrogen fuel from the interstellar medium as the spacecraft travels, theoretically providing limitless fuel. First proposed by Robert W. Bussard, this concept elegantly sidesteps the problem of carrying fuel. However, the density of hydrogen in the interstellar medium is incredibly sparse, typically just 1 atom per cubic centimetre. To collect enough fuel for meaningful acceleration, a ramjet would need a magnetic scoop kilometres, or even thousands of kilometres in diameter. generating immense drag. The energy required to maintain such a massive magnetic field, to compress and fuse the collected hydrogen, would likely exceed the energy gained from the fusion reaction itself. Furthermore, ramjets would only function optimally in regions of the interstellar medium dense enough to provide sufficient fuel, leaving vast cosmic deserts utterly impassable. The efficiency problem and the immense drag render this concept, while elegant in theory, practically impossible. What about breaking the rules of physics entirely? Concepts like warp drives, popularized by science fiction, aim to circumvent the speed limit by distorting space-time itself. Instead of moving through space, a warp drive would theoretically compress space in front of the ship and expand it behind, allowing the vessel to effectively travel faster than light relative to distant points, while locally remaining within the light speed limit. The most famous theoretical model, the Alcubierre drive, relies on exotic matter with negative energy density to achieve this feat. The problem? Exotic matter has never been observed, and its existence is purely hypothetical. Even if it did exist, the amount required to create a human-scale warp bubble would be astronomical, potentially exceeding the mass energy of an entire galaxy. Moreover, the physics of creating and controlling such space-time distortions are entirely unknown, if even possible. Warp drives are not an engineering problem. They are a fundamental physics problem requiring a revolution in our understanding of the universe that may never come. The reality, then, is that humanity is imprisoned by the very physics of propulsion. We can build bigger, more efficient engines, but they will always be bound by the light speed barrier, the increasing relativistic mass, and the insatiable demands of energy. Our current maximum velocity for a human-made object is the Parker Solar Probe, which reaches about 690,000 kilometers per hour. While impressive, this is less than 0.06% of the speed of light. To bridge the gap from a tiny fraction of a percent to even a significant percentage of c requires not just incremental improvements, but a violation of the laws of energy conservation on a cosmic scale. This propulsion's prison is more than just a technological setback. It's a cosmic chokehold. It ensures that our species remains confined to the minuscule fraction of the galaxy that is gravitationally bound to our sun, or perhaps, with centuries-long voyages, to a handful of nearby stars. The vast, glittering expanse of the cosmos remains forever out of reach, its myriad wonders observable but untouchable. The hopelessness comes from understanding that this isn't a temporary problem to be solved with more research or bigger budgets. It's a fundamental property of the universe, a permanent, unyielding barrier that defines the boundaries of human reach and casts a long, isolating shadow over our future. The very attempt to break free is met by an elegant yet brutal cosmic refusal. Even if humanity were to miraculously transcend the physical barriers of infinite mass and cosmic shrapnel, and reconcile with the temporal schisms of time dilation, a far more insidious and relentless prison awaits, the expanding universe itself. This isn't a static, boundless cosmos we inhabit, but a dynamic, accelerating expanse, actively pulling potential destinations away from us, effectively shrinking our reachable universe into an ever-tightening cage. The speed of light, our supposed pathway to the stars, becomes the very boundary of a shrinking cell, condemning future generations to an inescapable, profound cosmic isolation. For decades, astronomers have observed that the universe is not static, it is expanding. Galaxies are receding from one another, not by moving through space, but because the very fabric of space between them is stretching. This fundamental discovery, initially made by Edwin Hubble, revealed a universe born from a cataclysmic beginning, a big bang that set the cosmos in motion. For a time, scientists believed this expansion would eventually slow down, perhaps even reverse, under the gravitational pull of all the matter within it. The universe's fate was seen as a tug-of-war between expansion and gravity. Then came the shocking revelation of the late 1990s. The universe's expansion isn't slowing down, it's accelerating. This acceleration is driven by a mysterious ubiquitous force permeating all of space, a cosmic anti-gravity known as dark energy. Dark energy comprises roughly 68% of the universe's total energy content, and its relentless, repulsive pressure ensures that the stretching of space is not merely happening, but speeding up. This cosmic acceleration fundamentally redefines our understanding of our place in the universe, transforming the vastness into a diminishing prospect. The concept of the observable universe is critical here. It refers to the spherical region of space from which light has had time to reach us since the Big Bang. Currently, this sphere has an estimated radius of about 46.5 billion light-years, making its diameter approximately 93 billion light-years. This is the extent of what we can see, the furthest reaches from which information, travelling at light speed, has had enough time to arrive at our telescopes. But what we can see is not what we can reach, and the observable universe is not a fixed boundary, but a dynamic receding horizon. The problem lies in the ongoing, accelerated expansion. While light from a distant galaxy might be currently reaching us, that galaxy is also receding. If the rate of recession due to cosmic expansion exceeds the speed of light, then even a photon launch from that galaxy today towards Earth would never reach us. It would forever fall behind the expanding space, a cosmic race where the finish line keeps moving away faster than the runner. This defines a cosmic event horizon, a boundary beyond which events can no longer affect us no matter how long we wait. Crucially, this event horizon is not static. It is shrinking, relative to us, in terms of the number of galaxies whose light can eventually reach us. Galaxies that are currently observable, whose ancient light we are now receiving, will eventually accelerate away from us to such an extent that any future light they emit will never bridge the expanding gap. They will simply fade from our view, their light redshifted into invisibility, swallowed by the relentless stretching of space-time. The universe, in effect, is actively pulling away its distant inhabitants, sealing them off from us, one galaxy at a time. Imagine a future civilization, billions of years hence still residing in our corner of the cosmos. Their sky would be dramatically different from ours. Many of the distant galaxies we marvel at today would have long since disappeared beyond their cosmic event horizon. Their observable universe would be a much smaller, emptier sphere, containing only gravitationally bound clusters like our own local group, slowly merging into one super galaxy. They would have no evidence of the Big Bang, no cosmic microwave background radiation to detect, no distant supernovae to measure cosmic expansion. Their cosmology would be fundamentally different, possibly leading them to conclude they live in a static island universe, forever unaware of the vaster dynamic cosmos that once existed beyond their immediate reach. This is the ultimate expression of cosmic claustrophobia and hopelessness. The universe isn't just vast, it's actively sealing itself off, fragmenting into isolated pockets of matter. Our current window into the deep cosmos is a fleeting moment in cosmic history. We are privileged to see a richly structured universe, but this privilege is temporary. The accelerating expansion acts as an expanding cage, a dynamic prison that slowly but surely reduces our cosmic neighbourhood, making us permanent residents of an increasingly desolate island. The stars we now yearn to reach, the potential civilizations we seek to contact, are not merely distant. Many are being actively, irrevocably pulled away from us, receding into a realm of eternal inaccessibility. Even the most advanced theoretical propulsion systems, like hypothetical warp drives, cannot fundamentally escape this expanding cage. While a warp drive might allow for faster-than-light travel within our local, gravitationally bound cluster, it cannot counteract the expansion of space itself on cosmological scales. It might shorten the subjective journey, but it cannot bring back galaxies that have already receded beyond our event horizon. The universe's accelerating expansion dictates that, even if we could cheat the speed of light locally, the overwhelming majority of the cosmos would remain forever beyond our causal reach. A cruel reminder of our ultimate confinement. The long-term implications are bleak. As dark energy continues its relentless work, the universe moves towards a big freeze or heat death scenario. Galaxies will become increasingly isolated, stars will burn out, and black holes will eventually evaporate. The cosmos will be a cold, dark, empty void, with the scattered remnants of matter slowly dissipating. Our expanding cage is not just shrinking our view, it's driving the universe towards a state of ultimate, profound emptiness, a future where the concept of interstellar travel becomes not just impossible, but meaningless. The speed of light, therefore, is not just a limit to our current technology, but a fundamental constraint that defines humanity's ultimate, unyielding cosmic destiny of isolation. Having confronted the unyielding prison bars of infinite mass, time's cruel distortion, cosmic shrapnel, and the relentless expansion that shrinks our observable universe, the human imagination, ever hopeful, invariably turns to the fantastical, warp drives and wormholes. These concepts, staples of science fiction, offer tantalizing visions of escaping the light speed limit, promising to shatter our cosmic confinement. Yet, upon closer inspection, they reveal themselves to be not viable pathways to the stars, but rather illusions, fiction's false hope, predicated on physics that either remains purely speculative or violates fundamental known laws, ultimately deepening our sense of cosmic claustrophobia. The allure of the warp drive, famously depicted in Star Trek, lies in its elegant sidestepping of Einstein's speed limit. Instead of accelerating a spacecraft through space to faster-than-light velocities, an impossibility for anything with mass, a warp drive would theoretically manipulate space-time itself. It would achieve this by contracting space in front of the vessel and expanding space behind it, creating a warp bubble within which the spacecraft itself remains stationary or travels at sublight speeds. The bubble, and thus the ship within it, would then effectively traverse astronomical distances in a fraction of the time light would take, without violating the local speed limit within the bubble. The most well-known theoretical framework for a warp drive is the Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994. Building upon Einstein's general theory of relativity, which describes gravity as the curvature of space-time, Alcubierre demonstrated that such a manipulation could be mathematically consistent with the equations. However, the catch is monumental. To create such a warp bubble, the theory requires exotic matter, or negative energy density. This isn't just a rare element, it's a form of matter with properties fundamentally alien to anything we have ever observed or theorized to exist in abundance. It would possess negative mass, or at least negative pressure, allowing it to warp space-time in a way that normal matter, which only ever warps space positively, creating gravity, cannot. The amount of exotic matter required for even a microscopic warp bubble, let alone one large enough to house a starship, is astronomically vast. Initial calculations suggested an amount equivalent to the mass of Jupiter, later refined to amounts comparable to a few hundred kilograms. But even these optimistic figures are wildly speculative, assuming the existence and availability of matter we don't know how to create or control. The very concept of negative energy density itself poses profound challenges to quantum field theory and the energy conditions that underpin our understanding of the universe. It hints at a violation of fundamental principles, pushing the warp drive firmly into the realm of theoretical fantasy rather than practical engineering. Even if exotic matter could be harnessed, the problems don't end there. The creation and dissipation of a warp bubble would likely generate immense amounts of radiation, potentially incinerating anything in the ship's path upon arrival, and creating a violent shockwave for any observer at the destination. Furthermore, controlling the bubble, steering it, and turning it off precisely at the desired destination without ripping space-time apart are engineering challenges of an unimaginable scale. The Alcubierre drive, while a fascinating mathematical exercise, remains a distant, perhaps impossible dream, a tantalizing whisper of freedom that the universe seems determined to silence. Wormholes, another favorite of speculative fiction, offer a different theoretical escape. A wormhole, or Einstein-Rosen bridge, is a hypothetical shortcut through space-time, connecting two distant points in the universe, or even two different universes. Instead of traversing the vast expanse between two locations, one could simply pass through a tunnel in space-time, appearing at the destination almost instantaneously. This would effectively overcome the light speed barrier by shortening the distance, not by exceeding c locally. Again, the concept is mathematically consistent with general relativity. However, just like warp drives, stable, traversable wormholes also require exotic matter with negative energy density to keep their mouths open. Without this exotic matter, a wormhole would instantly collapse, likely into a black hole the moment it formed, making any passage impossible. Furthermore, creating a wormhole would likely require immense gravitational forces, potentially generated by black holes themselves, and the process of connecting two specific points in the universe, let alone to arbitrary points, is entirely unknown. Detecting naturally occurring wormholes, if they exist, would also be an incredible feat, as their gravitational signatures would likely be indistinguishable from black holes. The very existence of these shortcuts also raises profound causal paradoxes. If wormholes could connect arbitrary points in space and time, they could potentially allow for time travel, leading to the infamous grandfather paradox, where one could go back in time and prevent their own birth. While theoretical physicists grapple with such paradoxes, often proposing chronology protection conjectures that would prevent such violations, their very possibility underscores the extreme, potentially universe-shattering implications of wormhole travel. The universe, in its elegant self-consistency, might simply forbid such shortcuts to preserve causality. These hypothetical engines, while inspiring, offer a false hope, a temporary reprieve from the crushing reality of our cosmic confinement. They represent not a breakthrough, but a desperate yearning to break free from the fundamental laws that govern our existence. The fact that all viable theoretical solutions rely on the existence of unobserved, potentially impossible forms of matter or energy only reinforces the profound hopelessness of our situation. We are not merely limited by our current technology, we are limited by the very fundamental physics that defines what is possible. The narrative of warp drives and wormholes, while essential for captivating storytelling, ultimately distracts from the deeper, more unsettling truth. The universe has imposed ironclad rules, and it offers no easy way out. The speed of light is not a suggestion, it is a law, and every attempt to circumvent it, even in the realm of theoretical physics, invariably leads to the same intractable problems: infinite energy, exotic matter, and a violation of causality. This realization that our grandest aspirations for interstellar travel are likely consigned to the realm of fiction serves only to deepen the dreams. The universe has already drawn its impenetrable prison walls. The tantalizing dreams of warp drives and wormholes, born from the fervent reaches of human imagination, ultimately dissolve under the harsh, immutable glare of reality. They are but spectral echoes of a desire to transcend, whispers of freedom in a universe that has already pronounced its sentence. For at the heart of every cosmic ambition and every interstellar fantasy lies the ultimate, unyielding constraint: the speed of light. It is not merely a speed, nor just a limit. It is the fundamental, immutable law that dictates the very architecture of our existence, an unbreakable lock on the cosmic cage that binds humanity. This absolute constant, c, not merely a number, physicists strive to measure with increasing precision. It is the cosmic axiom, the bedrock upon which the entirety of Einstein's theory of special relativity is built. This isn't a rule imposed by a higher power, it's a property inherent to the very fabric of space-time itself. Every fundamental particle, every force carrier, every ripple of energy, from the faint cosmic microwave background to the blinding flash of a supernova, adheres to this speed. It is the universal tempo, the rhythm of causality, ensuring that effects never precede their causes, preserving the logical flow of the cosmos. To violate it is not just to break a physical law, but to unravel the very coherence of reality. The cumulative weight of this immutable law manifests in the paradoxes we have explored, each a reinforcing bar in our cosmic prison. First, there is the infinite mass wall. As any object with rest mass accelerates towards c, its inertial mass does not merely increase, it rockets towards infinity. This isn't a gain of physical matter, but a relativistic consequence where kinetic energy transforms into an ever-increasing resistance to further acceleration. To reach light speed, even a single proton would require an infinite amount of energy. A resource physical barrier ensures that no material object, no starship, no human body, can ever truly attain the ultimate velocity. It is an energy debt that can never be repaid, a cosmic bank account that will always remain infinitely overdrawn. Then comes time's cruel distortion, the relentless ticking of the relativistic clock. For any traveller approaching light speed, time itself would slow down relative to a stationary observer. A journey that subjectively feels like years could mean centuries or millennia have passed for those left behind on Earth. This isn't an inconvenience, it's an existential severance. It means that any truly distant interstellar voyage, is a one-way trip into an alien future, a journey where all connections to one's past, one's culture, one's loved ones are irrevocably. A galactic empire becomes a collection of temporal islands, each drifting into its own future, incapable of synchronous interaction or shared evolution. The threads of human connection are simply too short to span the relativistic gulfs. The vast, seemingly empty interstellar void, far from being a serene highway, transforms into a lethal gauntlet of cosmic shrapnel. At relativistic velocities, even the most microscopic speck of dust, a stray hydrogen atom, or a grain of ice, possesses kinetic energy, equivalent to a high explosive projectile. A starship moving be constantly bombarded by these hypervelocity impacts, each capable of vaporizing hull sections, degrading systems, and ultimately leading to catastrophic failure. No known material, no hypothetical energy shield could withstand such a ceaseless high-energy barrage. The vacuum of space, in its terrifying indifference, becomes an active, implacable enemy, turning the journey itself into a prolonged, agonizing suicide mission. And finally, the insidious, expanding cage of the accelerating universe. Propelled by dark energy, the very fabric of space is stretching, actively pulling distant galaxies away from us at ever-increasing speeds. This means that many of the galaxies we observe today, their ancient light having just reached us, are already receding faster than the speed of light. Any future light they emit will never reach us. The cosmic event horizon is shrinking, ensuring that billions of years from now, our descendants will gaze upon an increasingly empty sky, cosmologically isolated, cut off from the vast majority of the universe we currently perceive. The speed of light, our only window to this grand spectacle, paradoxically defines the boundary of an accelerating, irreversible retreat into cosmic solitude. These are not merely a collection of isolated problems to be overcome with future technology. They are interconnected consequences stemming from a single fundamental law, light's immutable speed. This law, woven into the very fabric of space-time, represents an absolute non-negotiable decree. It is the ultimate constraint, a cosmic refusal that transcends engineering, biology, and even philosophical aspirations. There are no loopholes, no clever workarounds that can bend these laws to our will without violating the very consistency of the universe. The dreams of faster-than-light travel, of interstellar colonization, of a truly galactic civilization are therefore not merely difficult but existentially impossible. This profound realization casts a long, isolating shadow over humanity's place in the cosmos. We are not destined to conquer the stars but to witness them from an unbridgeable distance. Our ambition, boundless and fierce, is met by an elegant yet absolute cosmic refusal. The universe, in its breathtaking beauty and terrifying scale, has erected an invisible prison around us, built from the very laws that govern its existence. The speed of light is not a horizon to be crossed, but an unyielding, unbreakable barrier, condemning humanity to a permanent, profound sense of cosmic claustrophobia within the confines of our stellar island. This is light's immutable law, and it is the ultimate, inescapable truth of our confinement. We have journeyed through the stark, unyielding truths that define humanity's place in the vast cosmic theatre. From the theoretical elegance of Einstein's equations, a tapestry woven with the fabric of space-time itself, to the brutal, practical realities of interstellar travel, we have seen how the speed of light, c, stands not merely as a boundary, but as an absolute, impenetrable prison wall around our species. This isn't a temporary inconvenience awaiting a technological breakthrough. It is a fundamental existential decree etched into the very core of physical reality, profoundly shaping our destiny. We confronted the infinite mass wall, the relativistic consequence that demands an endless supply of energy to accelerate anything with rest mass towards light speed, engines or harnessing more efficient fuels. It is an intrinsic property of mass and energy, ensuring that the universe itself will never yield the infinite power required to propel even a single atom to sea. Our grandest ambitions of star-spanning fleets, of vast interstellar empires, are thus extinguished by an insurmountable energy debt that can never be paid, leaving us forever tethered to our local cosmic shore. Then we wrestled with that slows for the Voyager, but not for the homeworld. A subjective journey of years across light years translates into decades, centuries, or even millennia for those left behind. This temporal chasm ensures that any physical return from a distant star would be a reunion with ghosts, a re-entry into a future that has marched on, unrecognizable and detached. The fabric of human connection, woven through shared time and experience, is irrevocably shredded by the very act of approaching relativistic velocities. It condemns any widespread human civilization to fragmentation, a collection of disparate cultural islands adrift in their own asynchronous timelines, forever severed from their origins. We peered into the terrifying reality of cosmic shrapnel, where the seemingly benign emptiness of interstellar space transforms into a gauntlet of hypervelocity projectiles. At speeds approaching CE, even a single hydrogen atom or a microscopic dust grain wields the destructive power of a bomb, capable of obliterating a starship and its crew. No shield, no material known or imagined, can withstand such impacts without catastrophic failure. The tranquil vacuum becomes an active, implacable enemy, relentlessly eroding and annihilating any vessel foolish enough to challenge its indifference, turning interstellar journeys into prolonged, agonizing acts of self-immolation. We acknowledge the expanding cages of our accelerating universe, driven by the enigmatic force of dark energy. This expansion actively pulls distant galaxies away from us, many already receding faster than light, ensuring that their future light will never reach our telescopes. The observable universe, far from being a boundless frontier, is a shrinking bubble, a temporary window into a cosmos that is slowly but inexorably sealing itself off. Future civilizations, billions of years hence. Our privilege of seeing a richly structured cosmos is fleeting, a temporary reprieve before we are all condemned to ultimate, profound cosmic solitude. And finally, we confronted our fiction's false hope. The seductive but ultimately unattainable visions of warp drives and wormholes. While mathematically intriguing, these concepts rely on the existence of exotic matter with negative energy density, a substance entirely unknown and perhaps impossible within the known laws of physics. Even if it existed, the energy requirements would be astronomical, and the causal paradoxes they invite threaten the very consistency of reality. These are not engineering challenges, they are fundamental physics problems materialize, serving only to deepen the profound sense of hopelessness that underpins our interstellar dreams. The ultimate constraint is therefore not a single barrier, but a convergence of unyielding physical laws, each reinforcing the other, forming an unbreakable prison. The speed of light is not merely a number, it is a cosmic pronouncement, an immutable law that defines the very boundaries of human aspiration. It ensures that while our minds may soar across light years, our physical bodies and our fragile civilizations remain tethered, forever bound to a minuscule speck in an incomprehensibly vast cosmos. This realization is for many a source of profound cosmic claustrophobia. The boundless universe, once a canvas for limitless dreams, shrinks into an elegant but inescapable cage. The grand narrative of galactic exploration, of humanity scattering its seeds among the stars, gives way to a more somber, perhaps more mature understanding of our place. We are, it seems, forever bound to our solar system, or at best, to a handful of nearby stars that we might reach only through multi-generational voyages, severing ties with our past. The loneliness that permeates the void is not just a spatial emptiness, but an existential truth. We are, and likely will remain, fundamentally alone in our corner of the universe. Yet, perhaps there is a strange stoic beauty in this confinement. If the universe truly has drawn such an absolute line, it forces us to reconsider our definition of exploration and progress. Perhaps true advancement lies not in breaking the unbreakable laws, but in understanding them, accepting them, and finding profound meaning within their elegant strictures. Our greatest journey may not be across the light years, but inward,